Okay, and in this part of this class or lecture, we will talk a little bit about some of the concepts or ideas that or examples of the distribution in protein binding, and it's just let's say concepts or equations from here and there that you need to take it into consideration. Again, we mentioned that, and this part we were explaining it in more details before, and then I cut major parts of it, but because I just want you to take the concepts out of the whole thing. So we mentioned that the distribution could be perfusion, perfusion limited, in which the perfusion is the rate limiting step, not the permeability. And we have a direct correlation, and we mentioned that before, between the flow rate or the perfusion rate and the time needed to reach the distribution equilibrium. Okay, and as the flow rate is increases, so the time needed to reach the distribution equilibrium as less, or let's say faster. Okay, if we are talking about direct relationship, so it will be faster to reach the distribution equilibrium. Okay, and then for the permeability rate limitation, then we have the limitation of the cell membrane, and now it's not perfusion anymore, so it jumped to be related to the penetration or permeability into tissues, and everything that you know about the transport or permeability that we know already would be factors that would affect the permeability, and at the end would affect the distribution and its equilibrium. Okay. Okay, and this case we have the ratio. Just let's focus here a little bit on the y-axis. We have ratio of the drug concentration, okay, in the cerebrospinal fluid over plasma, so in tissue over a plasma. Let me just talk about this ratio in a bit, or in a minute, in a second, in which it's again it's a ratio of the drug concentration in tissues over and plasma. Okay, this is called also, there's so many terms or the same definitions, the same thing for different terms. We have the tissue to blood, and it could be also plasma, equilibrium, distribution ratio, okay, which could be also as CT over CB, and the venous, in the tissue versus in the venous, which is in blood, could be also called tissue to blood ratio, as for short. Could be also called the affinity. Sometimes it's called also K from partitioning. Okay, all of those factors, it's related to its ratio. First of all, its ratio, so it's unitless. It's giving us the idea of the affinity of the drug in tissue compared to the blood, and we are just having it on y-axis. And again, we will talk a bit on about this ratio, which you already have it before in one term, but we will talk about it in a couple of minutes. Okay, so we have the ratio of the drug concentration in tissues over a plasma, which again it's related to affinity or distribution ratio or equilibrium ratio. Okay, So we have it for versus time, okay, for different drugs. So start with thiopental, we have pentobarbital, barbital, and salicylic acid. If we notice the behavior of each one of them, happens very fast, and then we reach the plateau, and then it start to be different. It start to be, let's use, okay, it start to be different for pentobarbital because we needed more time to reach the equilibrium or the plateau. Then it's later here, and we didn't reach it within, let's say, the time that we are showing for salicylic acid. Okay. If we are talking about the thiopental, it's perfusion limited because there's no resistance or no rate limiting of the permeability of the drug. That's why we reached the plateau directly, and it was fast as if we are talking about time. Okay, if we compare whatever is happening from here to there, let's talk about salicylic acid and pentobarbital. We can find that the lipophilicity of both of them are similar. Okay, and we know that we can talk about the lipophilicity of the drug according or using the partition coefficient. Okay, so the lipophilicity of both of them are similar, but the time required to reach the equilibrium for the pentobarbital, okay, is shorter than that for salicylic acid. And we can see here, according to the profile, we didn't reach it here. Okay, when we compare the physicochemical properties of pentobarbital compared to salicylic acid, we can find that pentobarbital pKa is higher than that for the salicylic acid, which means that we have higher or greater fraction of pentobarbital as unionized, which make it easier for it to pass for sure at the pH of the tissue that we are talking about, which is 7.4, which make it easier for pentobarbital to be to permeate through the tissue that we have. So the distribution equilibrium was reached faster. Sorry. Okay, so we need to take, see, this is an example that we need to take different factors into consideration, because if we take lipophilicity only, it won't work and won't explain what is happening. But if we take into consideration the ionization status, we can determine, yes, this is happening because of the unionized fraction of pentobarbital is larger than that of salicylic acid. Okay, and this slide, I'm showing you, let's say, a figure in which, if we are talking of volume distribution for different drugs, we can see that it could range between a 3 liter to very large volume distribution that would reach 40,000 liter. And again, it's as small as the plasma volume, as large as it can be because of the distribution to different tissues. Okay, and for sure, if we are talking about different protein binding, not one only, so we have different equilibrium according to the protein binding and the affinity to it. If we have different tissue distribution, then we have multiple equilibrium. So until now, we are talking about the distribution as affected by only, let's say, albumin binding or just distribution to the brain. But in the real cases, we have many factors that we need to take it into consideration, and maybe the drug itself binds to multiple plasma protein at the same time with different percentages, and we need to take all that into consideration. Okay, at equilibrium, and again at distribution equilibrium, which is very important as a point, we can determine the fraction of the drug in the plasma and the fraction of the drug outside the plasma by knowing, if we are taking that in the terms of volume distribution, by knowing the amount of the drug in the plasma over total amount in the body. Amount in the plasma could be determined by the volume of the plasma multiplied by the concentration of the drug in the plasma. Total amount, remember it's apparent volume distribution multiplied to concentration in the plasma. We can take those out. It will be volume in the plasma, volume of the apparent volume distribution of the plasma over the apparent volume distribution, total volume distribution. And again, in other words, that I'm taking it in terms of volumes. Okay, and for sure this would be 1 minus this fraction, which is n plasma, or in other words, this one would be 1 minus plasma over volume distribution volume, and which is the same as this term. Okay, and for sure, if we have more fraction, let's say fraction of the drug in the plasma, okay, it means that I will have more total apparent volume distribution and vice versa. Okay, it's just a way of math equation in terms of volumes to determine the fraction of the drug in the plasma and outside the plasma. Okay, this is a physiological way of thinking or talking about the volume distribution overall. Okay, so if we are talking again about distribution equilibrium, we will have a balance, mass balance equation in which the amount in the body, which is total, right, equals the amount in the plasma, right, plus the amount in the tissues. Okay, let's consider that we are talking about one of them. Okay, so the amount in the plasma would be volume of the plasma multiplied concentration in the plasma plus the volume in the tissue multiplied to the concentration in the tissue. Okay, we mentioned that this partition equals concentration in the tissue over concentration of the drug in the plasma. Okay, if we can't, which we know that we can't measure this easily for experimental reasons, it's not feasible, so I can just substitute this by the affinity or the distribution ratio multiplied to the concentration in the plasma, right? And again, I'm just mentioning it's the partition ratio or the distribution ratio, which is the same as I already mentioned. Okay, so again, it's the amount in the body, which is equal to this term. Okay, if we let me just write it from here, okay. So again, let me write it: mass balance equation at equilibrium, at distribution equilibrium, in which total amount equals amount in the plasma plus amount in the tissues. Okay, this would be equal to, if the amount over volume equal concentration. Okay, so total amount would be equal total volume multiplied to the concentration in the plasma would be equal concentration in the plasma volume of the plasma multiplied to the amount in the tissue, which would be equal to the concentration of tissue multiplied to the volume of the tissues, right? If we substitute this with, from knowing what I just mentioned here as partition ratio or affinity ratio or distribution equilibrium ratio multiplied to VT. Let's use different colors. 1 second. Okay, multiplied to the volume of the tissue plus we can notice that we have concentration in the plasma as a common factor here. So we can divide over C, concentration in the plasma. So at the end, I will have this, which is equal to, volume of the plasma plus the partition ratio multiplied to the volume of the tissues that we are talking about. It's similar to something that you already know, right? Or see, or I just mentioned, okay? So again, this is the total, this is what I just mentioned, okay? And this is the, both of them together, it's the apparent volume distribution to tissues from the measurement of the drug in the plasma, because we can't have this in terms of, as we mentioned, as concentration in the tissue. Okay, and if you have many tissues, for sure we will have the summation of all of those terms. Okay, and we will talk about this a little bit with one more idea in the coming minutes. Okay. For the binding within the blood, we know that we have a whole blood, we have cells, we have a plasma, we have serum. So the measurement that we have differs according to where I do the measurement. So if I did the concentration of the drug in the whole blood, again, the symbols I'm using here, it's the same symbols used in your reference, but could be different with different references, okay? And the plasma would be a C in the plasma, unbound or the free would be CU or CF, okay? We know that the unbound or free drug concentration, the one that would distribute and also the one would cause the activity, okay? The measured also, okay? But usually it's hard for us to measure the unbound concentration because it's the methods used for the unbound concentration is hard. So what we usually do, we could have measurement using different concentrations as I'm showing you here in this slide, but you need to take into consideration that we need to have the case of distribution equilibrium to be able to use those equations. So this is important to be at distribution equilibrium. Okay, other than that you can't use those kind of things. So if you measure the concentration of the drug in unbound or free and the plasma, okay, so the volume that you are measuring is the unbound volume distribution in the plasma. Okay, and as we are under equilibrium, we can use the amount of the body at equilibrium. Okay, another measurement, if we having the concentration of the drug in the whole blood, then the volume that we are measuring is the volume of the whole blood, a volume distribution of the whole blood. And again, we can use the amount as total amount in the body at equilibrium. And we can notice that amount of the body at equilibrium, okay, it's independent of the site of measurement. Either we are talking about total volume with a concentration in the plasma, or unbound or in the whole blood is independent of the site of measurement because we are talking about equilibrium, and that's why the amount in the body would be the same. Okay, in other words, when you have different volumes or different concentration at different sites, you need to use the corresponding volume, but you can still use the amount in the body at equilibrium because, again, which is XP, because we are under equilibrium. Okay, and this is one advantages of doing our measurement at distribution equilibrium. Okay, for the plasma protein binding, which we talked about it a little bit before, it's variable among a patient at different therapeutic setting, and we know that, and we mentioned that at different disease disorders, we have different protein binding fractions or percentages because we have different protein concentrations and affinities. Okay, the degree of the that we have expressed bound to total concentration ratio, which is usually the ratio from 0 to 1, and you need to make sure that we are talking about the bound drug or the unbound drug. Okay, and usually if the unbound the bound fraction is higher than 9 0.9 or 90% as a fraction 0.9 or 90%, we consider it as extensively bound drug or highly bound to protein. Okay, for the fraction here, it's percentage of unbound. Again, just be careful what we are talking about. It's a range from 0 or in this case 0.1 to 100, because we are talking about percentages. Okay, can we determine the fraction of the free drug in the plasma? Yes, you need to know the concentration of the unbound or free drug in the plasma over the total concentration in the plasma, right? If we consider the fraction unbound or the free fraction of the drug is constant, so we can use this equation to determine the changes of this term, right? So if this is constant, which is usually the case, we can use the concentration of the drug in the plasma, the total that we usually measure, to determine whatever the difference is of this, right? And this is what usually the case. And of course, if you have the fraction unbound of the drug, you can determine the fraction bound of the drug and vice versa, for sure. Okay. Okay, and this part, just focus what I'm saying, because I will ask about the concept in general and the calculation on one part, not all of it. But for a single binding site, which is usually the case of to understand the whole situation, we consider that we have a single binding site, which is not the case all the time. But just to understand it, we have drug that is associating with the protein with a reversible reaction to give us the drug protein complex. Okay, and again, with higher affinity, the equilibrium will move to the right, and with higher protein concentration, again, it will move to the right because it's equilibrium, and we know that. And if we want to determine the association constant, it will be equal the concentration of the product, okay, over the concentration of the reactant, right? So if we talk about kinetic terms, it will be concentration of bound drug, because it's drug protein, which is this one, okay? The concentration of the bound drug over the concentration of free drug, which is just drug concentration, which is free, over free protein, which is unbound protein, okay? And this is a free or unbound, okay? This is the reactant. Can we determine the fraction of unbound total number of binding sites on the protein? Yes, we can determine it, and don't be confused. This is unbound of the protein, okay? The fraction unbound of the protein total sites, okay? It would be equal to the unbound protein concentration over the total protein concentration, which is bound and unbound, okay? Again, we can determine the concentration of the free drug, concentration of the bound drug. We just mentioned that. Play around with the equations. You will have this equation to determine the fraction unbound of the drug. Again, it could be, if we are talking about factors, the concentration of the total protein, association constant, and the fraction of unoccupied sites of the protein. Again, this is our equation, and if we consider the common case, the binding sites are usually not saturated at therapeutic concentration when we are talking about what is we call it linear kinetics. So usually this fraction, which is the same as this one, okay, it's usually remains close to 1. So accordingly, the fraction unbound of the drug relatively depends on the association constant and the total concentration of the protein, which means this won't be changed and this won't be changed. So it's usually, if we are talking about the usual case, it's depends on the given protein concentration and the association constant, which again, it's not affected by the drug concentration. Okay? From this part, okay, until this part, I need you just to understand the overall thing as concepts. Okay? Do we have this as a general case or the other case that we will talk about it or not? Just as concept wise, but you need to know that we in different conditions similar to whatever we mentioned in the previous recorded video, that the protein concentration or the binding to the protein would be affected. Okay, so accordingly, if we consider this equation, okay, this equation, it's important to determine whatever is happening in the modified, or if we modified case, or in the altered situation compared to the normal or healthy. We can, by knowing the, let's say, the total protein concentration fraction unbound of the drug in the normal case, and let's say, for example, the whatever is happening to the total protein concentration and the disease case, we can know what is the fraction of unbound drug in that disease state. Okay, and this is important. Example of that, this question, and I know that you can do it by yourself, but let's do it quickly. If you know that the fraction of unbound of a drug, in this case ibuprofen, the fraction unbound equals to 0.005, okay, and the ibuprofen is bound to albumin. And diseases such as alcoholic cirrhosis, the concentration decreased of what? The albumin concentration from 43 to 28 gram per liter. So we have the protein total concentration that is equal in the normal case 43 gram per liter compared to the total protein concentration in the disease state, which is liver cirrhosis, that is equal to 28 gram per liter. Can you determine the fraction of unbound a drug unbound to albumin in the alcoholic cirrhosis case? Yes, you can, by just knowing that, which is the one that I mentioned, and the fraction unbound of the drug. And we have this 0.005, this as 43, and this as the one that we want, and this as 28. And we have the same unit, so we are fine. And then the fraction would be 0.007 or 7.7 multiplied to 10 to the power of minus 3. Okay, what would be the percentage of change? Okay, this would be the percentage. How we got it, because it's a percentage of change, would be what is the new fraction minus the original over, right, multiplied to 100%, because you are asking about the percentage of change. And this is how you got it. Okay, and this diagram, I'm showing you the effect of the first of all, we have alpha-1 acid glycoprotein concentration, which is again protein concentration, fraction unbound, which is this fraction unbound of the drug, and the drug that we are talking about is propranolol, okay, which is the binding protein of it is alpha-1 acid glycoprotein. And we can see from here that we have it for healthy volunteer, which is diamond, compared to cirrhosis, renal diseases, arthritis, and Crohn's disease. And we can notice that with different, let's say, cases, different disorders, different situations, or the disorders or the pathology of is affecting the percentage that we are talking about. So accordingly, the fraction of the M bound of propranolol is different. And again, all of that data from different studies to show the effect of that. Again, we mentioned that generally, the binding site is not saturated, so the fraction unbound of the protein, overall of the protein, is close to 1, but sometimes the therapeutic concentration are not sufficiently high so that most of the available binding sites are occupied, are sufficiently high. Did I say not? They are high. So sometimes the concentration according to the unoccupied sites are high, so they are totally occupied. So we can reach a point in which we are talking about nonlinear kinetic, in which both either the fraction unbound of the drug or even the fraction of the unoccupied sites of the protein is concentration dependent, so we can't take it as close to 1. Okay, so usually it's linear kinetic, but sometimes if it's all of them are occupied, so we can reach to the nonlinearity, and then the fraction unbound of the drug start to be concentration dependent. Okay. For the tissue distribution and tissue binding, before we were talking about the plasma binding almost or most of the time, but if we are looking at it, the distribution to tissues from tissue binding point of view, again, if we have, remember the one example that we got, or I gave to you at the first when we were talking about systemic circulation and tissues or organs. Remember that? And we were talking about whatever is happening for volume distribution. And we mentioned that if we have more binding to tissue proteins, then the drug would go more into the organs compared to systemic circulation. The same thing that I'm talking about here, if we have a higher affinity of the drug to tissue proteins, then I'm mentioning if it's have a great affinity for plasma protein, but still located mainly in tissues, if have a greater affinity to tissue protein than to plasma protein, which means I may have here binding to plasma protein of the drug, but the affinity here is larger than that for the plasma protein. So that's why I will find the drug more into distributed to organs compared to systemic circulation, and that's related to the affinity of the drug to the protein. Okay. We have problem, as we mentioned before. We can't measure the concentration or the amount of the drug in the tissues because of the problem of the experimental problem. It's not feasible. That's why we need to go around it in a different way that is related to a place or a measured samples that we can measure. So what we can use whatever that we know in the plasma to determine tissue binding in a mass balance equation, similar to whatever I mentioned, but we are taking into consideration volume in tissue, taking into consideration the aqueous volume outside of the plasma in which the drug is distributed. And if we are talking about kinetic, if the volume that is the drug is distributed outside the plasma, then would be almost similar to the volume of distribution of a band volume distribution to the tissues. And concentration of TW as the drug concentration required to account for the mass of the drug in the tissue. Okay, And again, if you divide by CB, then the concentration in tissue over concentration in the plasma would be multiplied to the volume of the aqueous volume outside the plasma or in the tissue. Okay? Again, if this is the equation, if we go back to volume distribution equals VT multiplied, if you remember, fraction and bound in, right? Fraction and bound in tissues, which is the one that you already know, okay? Or the same one or similar one, multiplied to concentration tissue over concentration in the plasma, okay? Which is the same as this, okay? But different way to look at it. We can know that at equilibrium, just let's start from here, that the concentration tissue over plasma would be equal the fraction unbound in plasma over the one unbound in tissue, okay, if we are at equilibrium, okay? And so you can get this instead of the concentration term, so you can have it as fraction unbound over in the plasma over the unbound in tissue, which is the same thing that you know, okay? And again, before going into this diagram, this is what I was saying, or the idea that you need to get, that we can know that the ratio, distribution ratio, or partition ratio, or the affinity, which is equal to this term, is a measure of the relative binding of the drug between a plasma and tissue, which is an important point. So remember that what I mentioned in this slide, okay, which is equal to fraction unbound in plasma over fraction unbound and tissue is at equilibrium. So which is the tissue to blood or plasma equilibrium, okay? So again, from this, just take into consideration whatever, or just consider whatever I mentioned before, but you can take or remember that when we are talking about binding in tissues, that we can't measure it, we need other terms. So that's why we use the plasma data or something that we can measure to determine whatever is happening in tissues, okay? And here we have an example of a volume distribution of propranolol that mentioned as volume distribution, okay? Total volume distribution versus the fraction unbound in plasma, okay? And either in control or healthy subject versus chronic hepatic disease. And then if I give you this to study or give me an idea according to whatever you know of the physiological model of the volume, right? So if I'm showing you this, which is your y-axis, volume distribution, versus this, we can see that it's showing me almost a linear profile or directly proportional relationship, which give you an idea that whatever is those factor is the effect of those factors is constant, and the main factor affecting the whole thing is the fraction unbound in the plasma. And this is what I'm telling you here, the effect of the tissue volume and the tissue over the unbound fraction in the tissue is relatively constant. So account for the differences in the binding of the propranolol in the plasma accounts for the major variability and the volume distribution, which is here the total volume distribution, which is this, okay? And again, this is just a cases or study cases that you can give a conclusion out of it if you know the equation that we are talking about, okay? And again, the volume distribution would be different for bases compared to acids. Okay, so because we have different ionization profiles for each one of them, but it was found that the distribution of basic drugs are much larger than those usually. Okay, so usually it's much larger than that for weak acids. And when they tried to find why this was happening, first of all, if you look about directional diffusion, you can at physiological pH, you can get an idea that, okay, the ionization profile would help of that. And another thing, when they was testing or analyzing the tissue acidic phospholipids, which is a primary site for basic drugs, primary binding sites for basic drugs, when they start to find tissue to plasma concentration ratio, which is again the affinity ratio or K partition ratio, they was finding that the tissue to plasma concentration ratio is increasing with increasing the concentration of that protein or a phospholipid. And again, as it's a side primary sites for the basic drug, for binding to basic drugs, then it was found to be one of the major reasons why the distribution aberrant volume distribution for basic drugs is more than the weak acids. Okay, we have one question here. And again, it's an easy question as calculation-wise, but let's go. A volume distribution for a drug is 300 liter. This is volume distribution, 300 liter. The fraction unbound in the plasma equals 0.06, okay? And what is the plasma concentration when 30 milligram of the drug in the body? We have plasma concentration. If we are having 30 milligram with a total liter, then this would be 0.1 milligram per liter. This is something that you already know. Whatever would happen if the amount of the drug, if the concentration in the plasma equals 0.2 over 300, right? So 300 multiplied to 0.2, then the amount at that time in which we have 0.2 would be equal to 60 milligram. Okay, what is the percentage of the drug in the body, knowing that the volume of the plasma equals 30 liter in plasma and outside plasma? Once you were asked in plasma and outside plasma, then you go directly to the fraction of the in plasma in terms of volume, fraction outside plasma, right? And plasma would be equal to volume of the plasma over the volume total, which is volume distribution, okay? Which would be equal to 3 over 300. And this would be 1 over 100 if we are talking about percentage. Let me just remove this for now. If we are talking about percentage, so multiply to, this is percentage in plasma, multiplied to 100, this would be equal to 1%. Okay, the fraction outside of plasma would be 1 minus 1%, which would be equal to 99%. Again, easy breezy question, but it's okay. For this one, it's a question related to this equation, and it's direct substitution, so you would be able to determine it. Okay, and good luck.